Greetings all and welcome to your first lesson on linear analysis. So we're going to start in section 1.2 and we're going to look at some key terms that pertain to differential equations. The first one is differential equation. We'll define that. It's abbreviated DE. Then we'll talk about linear and nonlinear differential equations, homogeneous and non-homogeneous, and what initial value problem is. Okay, so what is a differential equation? Okay, a differential equation is an equation for an unknown function y that involves the derivative of the unknown function itself. Okay, so prior to now, our experience with equations deals with the unknown being a real number. Okay, think of x squared plus x minus 6 equals 0. We wanted to find the unknown number that solved that equation. Well, now we have an equation that has a function and its derivatives that solves an equation. For example, therefore, y double prime plus 2y equals 0. What function, when I take its derivative and I add back to it twice itself, do I get 0? Okay, well, whatever function that is, that's what solves the first differential equation. Now, if you prefer Leibniz's notation, which in this class I don't, you could write it as the third derivative of y, or y triple prime, plus 4y double prime plus sine x times y prime equals xy plus tangent x. And that's a perfectly fine differential equation. It's an ugly one, but it's a differential equation. Third one's a differential equation. Doesn't matter if y prime happens to be in the exponent. Okay, it doesn't matter. The fourth is another example of a differential equation. All right, so let's go to what is a linear term in the differential equation. A linear term has the property, as a distributive property, that basically L of y1 plus y2 is the same as L of y1 plus L of y2. Okay, let's see why that might be relevant here. Okay, so I'm saying to you that y double prime is a linear operator because if I take two functions and according to the operation L, I take the derivative of the sum of two functions. So I get y1 plus y2 double prime. What is that? Okay, well, if I were to take y1 plus y2 as a sum of two functions, and I were going to take two derivatives of that, I would get y double prime, y1 double prime, plus y2 double prime. I take the derivative of each of those independently, and this is what I would get. For this to be a linear operator, what I have to do is I have to say L of the sum is the same as the sum of L of each individual one. So this would mean, make sure it's still in the viewing window, yep. This says plug in y1 into the to the operator L, okay? That means take two derivatives of y1. What do you get? y1 double prime. To that, add two derivatives of y2. What do you get? You get y2 double prime. The question is what's here in red the same as what's here in green? The answer is yes. Since L of the sum is the sum of the L's, then this is a linear operator. Okay, so what is it? y1 prime squared is not a linear operator. Okay, so let's look at that. L of y1 plus y2. So what does the operator say? It says take the derivative and then square it. So what is this? We're going to take the derivative of y1 plus y2. And then after that, we square that result. So this is y1 prime plus y2 prime when you take the derivative of y1 plus y2. And now square that, you get y1 prime squared, you get y2 prime squared. But because of foiling, you get 2 times y1 prime times y2 prime. So the question is that equal to L of y1 plus L of y2? So according to our rule, we're going to take y1, take its derivative, we get y1 prime, and then square that result. Then we're going to take y2, take its derivative, square that result, and then add the two together. The question is what's in green here, or red here, the same as what's green there? And the answer is no, because we're lacking the 2y1 prime, y2 prime. Therefore, y1 prime squared is not a linear term. And any term in the differential equation not being linear makes the whole differential equation non-linear. Now, the order of a differential equation is the order of the highest derivative appearing in the differential equation. So, before we get to the next definition, okay, if we were to revisit all of the differential equations that we had on page 1, we look at order. Okay, what is the highest order of the derivative in equation 1? Well, we have y double prime, so the order of that would be 2. What about for equation 2? Well, we have y prime, we have y double prime, we have y triple prime, so the order of that differential equation would be 3. Here we have the first derivative and only the first derivative, that would be 1. And in number 4, we have y double prime, we have the fourth derivative of y, the order of this differential equation would be 4. Quiet, guys. Sorry, these are my chocolate labs that apparently just woke up. Okay, so moving back to another definition. A differential equation is homogeneous if the function y equals 0, so at any value of x. So y equals 0 solves the differential equation. If that's not the case, we say that the order of the differential, if that's not the case, we say the differential equation is non-homogeneous. Okay, so looking at the first example, let's get a fresh sheet of paper. Okay, if I were to plug in 0 for y double prime, so let y equals 0. What's y prime? 0. What's y double prime? That's also 0. So under this equation, you'd say y double prime, 0, plus 2 times y, 0. Is that equal to 0? The answer is yes. So this is a homogeneous differential equation. Okay, what about 2? Okay, if y equals 0, okay, and then y prime equals 0, y double prime equals 0, y triple prime equals 0. So that's all obvious, but it's not obvious where you can see it because I'm out of the viewing screen. There we go. Okay, and we were to plug this into equation 2. We'd get y triple prime, which is 0, plus 4 times y double prime, which is 0, plus the sign of x. Okay, notice that y is 0, not x, times y prime. Well, y prime is 0, so that will product to 0, bummer, equals x times y, well, we said y was 0, plus tan x. So that's 0, that's 0, that's 0. We get 0 equals, that's 0, that's the tangent of x. And is that true for an interval of x's? Nope, it's not equal to 0. So equation 2 is non-homogeneous. So we can kind of go through things maybe a little bit faster, okay? For equation 3, go back to red, we get the sine of x times e raised to y prime. Well, if y is 0, then y prime is 0, minus the tangent of 0 equals the cosine of x. So that's 1, so that's sine x, minus the tangent of 0, that's 0, equals the cosine of x. Does sine x equal cosine x? That's no. So this is non-homogeneous. And lastly, equation 4, we have, do it in green, what? Root x times 0 plus the natural log of x over 0 equals 3x cubed. Well, that's clearly non-homogeneous. Why can't it be 0? All right. So, identify each as linear or nonlinear. We haven't done that. Homogeneous or non-homogeneous. We have done that. And the order, we have done that. So next, we talk about whether or not the terms in each of the differential equations are homogeneous. Okay, we've already established that y double prime, sorry, I said homogeneous, I meant linear. We've already established that y double prime is a linear operator. In fact, so is y prime, because if I take y1 plus y2 prime, that is equal to y1 prime plus y2 prime. Okay, so the first derivative is a linear operator, the second derivative is a linear operator, the third, fourth, fifth, sixth, all the derivatives are linear operators themselves. Okay, we notice that when you take a linear operator and then you square it, it's not necessarily a linear operator. So just want to make sure I made that point. What about a constant times y? Okay, is that a linear operator? So in this case, the constant is 2. If I take 2 times y1 plus y2, I get 2y1 plus 2y2. Okay, and it does have that distributive effect that we talked about earlier. This is L of y1 plus y2. This is L of y1. This is L of y2. And this is the sum of L1 and L of y1 and L of y2. Therefore, a constant, multiplicative constant times y is a linear operator. One of the other things is what happens if you're multiplying with y by a function of x. So let's say that L of y is f of x times y. Is that a linear operator? I'll draw a line to kind of differentiate the ideas. Okay, so pick your favorite function of x. Okay, right now I'll say it's the sine of x. That's acting as f of x. So what is L of y1 plus y2? Okay, that's equal to the sine of x times y1 plus y2. What's L of y1? That's the sine of x times y1. What's L of y2? That's the sine of x times y2. And what is the sum of L of y1 and L of y2? So that's the sine of x times y1 plus the sine of x times y2. And the question is, that's L of y1 plus L of y2. Question is this equal to L of y1 plus L of y1 plus y2? So is what's in red right here the same as what's in red right there? And the answer is yes, it is. That's great. So now I picked the sine of x at random, okay? What if you picked cosine x? What if you picked e to the x? What if you picked x or x squared or x cubed? Does that change the basic overall process of showing that this is a linear operator? And the answer is no. Okay, it doesn't matter what function of x I put right here. Okay, this will be a linear operator. So that will make things go a little quicker. Okay, so I'm just going to put an L or I'm just going to say whether a term in the equation is linear or not. Okay, y double prime we said was a linear operator. A constant times y was a linear operator. So this is a sum of linear operators. So this is a linear differential equation. Okay. The third derivative we said was a linear operator. 4 times the second derivative, so constant times the second derivative is a linear operator. A function times y prime, we just established that that was a linear operator, equals a function of x times y, that will be a linear operator, plus tan x. Okay, well, this doesn't involve y, so it's going to be linear in term with respect to y. So all of this means that equation 2 is a linear differential equation. Okay, what about equation 3? The sine of x times e to the y prime. Okay, so let's look at e to the y prime. E, so L of y equals e to the y prime. What's L of y1 plus y2? Well, that's e raised to the derivative of y1 plus y2. So that's e to y1 prime plus y2 prime. So is that equal to L of y1 plus L of y2? So that's e to the y1 prime plus e to the y2 prime. So is everything that's right here underlined in red the same as everything that's underlined in red above? And the answer is no, it's not. Because remember, this sum, even though I kind of wrote it sloppily, is in the exponent. So by rules of exponentials, this is equal to e to the y1 prime times e to the y2 prime, which is different than plus e to the y1 prime plus e to the y2 prime. So this is not linear. Okay, so because one term in the differential equation is nonlinear, then the whole thing is nonlinear. Looking at equation number 4, okay, we have root x times the fourth derivative of y. Well, we know that that is a linear term, plus the natural log divided by y double prime. Is that a nonlinear term or is it a linear term? Let's take a look. So we have what? L of y equals log x over y double prime. So L of y1 plus y2 is equal to the natural log of x divided by y1 plus y2 double prime. Is that equal to L of y1 plus L of y2, which would be the natural log of x over y1 double prime plus the natural log of x over y2 double prime. In other words, are you able to split up the denominator? Well, you know the answer to that. If I have A over B plus C, is that equal to A over B plus A over C? And the answer is, of course not. You can't split up a denominator. You can do it to the numerator, but if you could, then you'd have funny things happening like 1 over 1 plus 1 is 1 over 1 plus 1 over 1, which is 2, but 1 over 1 plus 1 is 1/2, and 1/2 is not 2. Okay, so this is not linear, and so the differential equation is not linear. Okay, so I'm gonna pause the video right now, and I will pick up the second group, set of notes right after this example.